if you go back and look at how I cover Physics 1 with Unit 2, no net force, Unit 3, net force, etc. And if you go back and you look at the College Board suggested pathways with Unit 1, kinematics, Unit 2, Unit 3, I don't remember all the various topic areas, you will see that force has been touched upon and covered in every one of those units, and so that's 6 units. We're going to cover torque, our rotational equivalent to we're going to cover torque, our rotational equivalent to force, in a part of a unit, and so it's a very we're going to keep it as a relatively high level discussion. A lot of kids have heard of torque. When I first introduce it, have you ever heard of torque? And they'll say, yeah. And I'll say, great. Where? And they'll say, a car commercial. And I went, you're right. And so I like to introduce it, and as I do with many things, I don't really get into the true technical definitions. I just give them away to. Torque is a rotational force. That's how a twisting force. A lot I hear defined that way sometimes. It's a twisting force. It is not force. However, a force is required to apply the torque, to supply the torque, and that's a pretty big idea. If we have an unbalanced force, if we have a net force, we're going to have a change in velocity, which is referred to as an acceleration, and we have kinematics. If we have an unbalanced torque, we have a change in angular velocity, which is an angular acceleration, and we can talk about rotational kinematics. So I introduce Unit 7A with rotational kinematics. I don't spend a whole lot of time on it. I do give some problems with it, more for practice than anything else. So let's jump into rotational kinematics. I don't spend a whole lot of time going over rotational kinematics. I might spend a class period introducing it. We might do a couple practice problems just to kind of convince them to it's the same as the previous kinematics. We use the same equations. Now, I say that they just have the different terms, the rotational motion symbols, but it's the exact same equations. What the number one rule is in kinematics, and the number one rule in kinematics is that the acceleration is constant. I remind them, or hopefully they will remind me, as to when you're using the kinematic equations, what the number one rule is. And hopefully they'll tell me the number one rule is acceleration must be constant. And I say, hey, same thing here. Torque must be constant. Angular acceleration must be constant so that we can use these kinematic expressions. I might introduce it. I'm not going to introduce the expressions here. They're exactly the same. You can look them up on the formula sheet. I do talk about some other terms that aren't immediately obvious. We talk about when the object is rotating at a constant speed, which means the net torque is 0. That the angular velocity is just the angular distance it goes divided by the time. Very similar to speed. Speed is the distance divided by time. Well, if we think about angular distance, and if we think about one rotation, that one rotation is 2 pi radians. And it makes this one rotation in a period. And so there's an expression of omega is 2 pi over period on the reference sheet that I want to make sure I talk about as to what it means, just as the average speed. We also talk about this thing, and it's called a rigid body. And basically, a rigid body is an object that's solid, that all the points spin together. The Earth is a rigid body. An egg would not be a rigid body. The yolk is liquidy. And so with a rigid body, all points along the radial have the same angular velocity. If you think about a merry-go-round, a carousel, all the horses make one revolution, 2 pi, in the same time period. All of them do. I tend to use the analogy of, we're in the South with the ceiling fans, and I say, if you look at the blade of the ceiling fan, it makes a full circle in the same amount of time, whether you're up close or whether you're far away. And if you think about it, I tell them, when you look at a ceiling fan, because I know they all have, and they try and follow it with their eyes, and it's easier to follow the blade part that's closer to the middle of the circle than the outside. And we talk about, well, that's because the outside part has a higher velocity. Keep in mind that velocity, or speed, is distance divided by time. And if we talk about going around in a circle, the distance we go in a circle is the arc length of a circle in some time period, t. So we make one full arc circle, I'll say, in a period. That would be r delta theta over period. This is angular velocity. And so one thing that's important that I think they need to recognize is that we have a relationship between linear speed and angular speed. The linear speed is r times angular speed. So the farther out you are along the radial line, you're going to be going faster, which makes sense if you think about the ceiling fan. The ends are traveling faster. It's harder to see than on the inside. There's a similar expression with that relates linear velocity with angular velocity. These equations are not on the formula sheet. Not really sure, I'll be honest with you, I'm not really sure how critical it is for them to know. They do need to know this idea and be able to explain points further out are traveling at a higher linear speed. So I don't spend a whole lot of time talking about rotational kinematics. I then jump into rotational inertia. Which is rotating mass. It's our rotational equivalent to mass. This is a very, this can be a really hard idea to understand. I introduce it this way. I'll be spinning a meter stick. And I'll ask somebody in class, can you do this? And I'm usually able to find somebody, and they come up and they go, okay, great, thank you. And then they sit down. I'm like, wait a minute, you're not done. Hold it here and spin it. And they'll be like, I'm actually doing okay with this. Then I'll go back to the middle, and they can go it a little bit easier. And I'll be like, what's the difference? And sometimes they give me a good answer right away, and sometimes they give me the best answer right away. And the best answer is, and I get this a couple of times, when they're holding it, I don't have much room in here. When they're trying to spin it like this, they'll say, it feels heavier. And I'll be like, that's perfect. It feels heavier. I'm going to hurt myself. It feels heavier. Is it heavier? It's the same weight. And so it's not heavier, but it does feel heavier. And that's a perfect definition. It has a different type of mass or whatever you want to talk about it. And so rotational inertia, and a lot of times they pick up on it. Well, I have more of the meter stick further away. Yeah, that's it exactly. Rotational inertia is based on mass distribution around turning point. That's a pretty fancy way of saying where's all the weight. The further away it is, the harder it's to turn. The closer it is, the easier it's to turn. That's rotational inertia. There is a calculation for it. It's not on the formula sheet. I don't like having the kids do it because, quite honestly, it's not as easy as they think it is. The more mass, the more mass from the turning point, the higher the rotational inertia. I have a colleague that would refer to this, that says higher. The higher the rotational inertia. I have a colleague that would refer to this as it's rotationally fat. So I tend to refer to that rotationally fat, and we're going to take a look at, and this plays a big role with angular momentum, by the way. I like to break it down much more simpler, and I like to have the kids think about it, because they're not going to be asked to. They're going to be asked to do some comparisons between objects, and so I ask them if it's harder to rotate because of where the mass is. If it's harder to rotate, it has a greater rotational inertia. If it's easier to rotate, it has less rotational inertia. If it's just like mass is, if an object is hard to move, it probably has a lot of mass. If an object is easier to move, it probably has less mass. Now there's other things that come into play, but let's think simply about it. So I said they're not going to get into doing calculations for it, but they do need to compare. They'll need to compare, what the rotational inertia is between similar objects. They're going to have to compare the rotational inertia. For example, let's say I have my meter stick, and my turning point's right here in the middle, and it's going to rotate this way. Or my turning point is at the end, and it's going to rotate this way. Or my turning point is through the stick, and it's going to turn this way. Which one has rank them from greatest to least rotational inertia? That's the type of question I think they need to be able to. That's what I'm talking about, compare rotational inertia. In which case, this is the hardest to turn. So this has the greatest rotational inertia. Comparing this, which is not that bad to turn, this is much easier to turn. My turning point's right here, in the middle of my meter stick. I don't have much mass. My mass is not far from it. So this is easiest to turn. This is going to have the lowest moment of inertia. This is going to be right in between. That's pretty much my discussion on rotational inertia. Now, let's jump into torque. I know this 7A is on torque, and it's taken me several days to get to the idea of what torque actually is. Because I have to introduce other terms first. We have to look at rotational kinematics. We did that before we really looked at forces. Mass is mass, but we have to talk about rotational inertia a little bit first. I talk about torque by introducing them to Newton's second law. Acceleration is net force divided by mass. And say we are analogous, and I remind them that's our word, analogous. Our term that's analogous to acceleration is angular acceleration. Our term that's analogous to torque or force is torque. And moment of inertia, rotational inertia. So these are the two equations. This is Newton's rotational second law, which means our net torque is I alpha. F is equal to ma. Now, we don't really use this expression. We use the relationship. Again, the math in this section is kind of, there's not a whole lot of math, quite honestly. Now, here's what they have to understand. In order to have a torque, we have to apply a force. And this is probably a source of a lot of confusion. And so I like to talk about the example with wrenches. So here we have a range of wrenches from small, maybe a 1/4 inch, to much bigger, maybe 7/8 inch. And the whole idea is simply that a smaller bolt to hold smaller items does not need as much torque. And so on a smaller bolt, we can't apply, it's hard to apply a lot of torque because, simply put, it's a smaller wrench. In other words, it is much easier to apply more torque on this bigger wrench because we can apply a big force at this end. My arrow is horrible. And we can to result in a big torque where the bolt head is. The wrench is thicker, it's longer from where the torque is, from where the bolt head is to where the force is being applied. That's what contributes to a larger torque. It's harder to apply a larger torque to a small bolt. Simply put, if we did, we'd likely strip the bolt. We need to apply more torque, we need to apply a greater force to get more torque with a bigger bolt. Again, a force is not a torque, but here's the thing. We have a wrench. I'm not going to do this. I'm just going to go this. This is my wrench. I know, it's pathetic. Here's my bolt. So I'm going to grab it here and I'm going to turn it to tighten it up. I'm going to apply a force downward in order to turn it. The distance from my turning point to where my force is being applied is referred to as my radial arm. So I get a greater torque by having my hand out further than in close. I get a greater torque by applying a greater force. So the torque is calculated by R times force. However, we only want the perpendicular component of the force. This is a little bit different than what's on the reference sheet, but that's okay. We end up with the same idea. To get only the perpendicular component, I take the sine of the angle. In other words, the angle between force and my radial arm is theta. Typically, it's 90 degrees. It does not have to be. I can easily see where they, some good ranking tasks or tippers would apply, we have this situation, we have a force like this. We have a force going straight out. We have a force being applied right here, and you rank all the different torques. Those are great exercises to do. I give those to my kids all the time. This is the expression that's on the formula sheet. It's also equal to I alpha. F equals ma is not on the formula sheet, but that guy is. I tend to focus my problems on rotational equilibrium. We talk about the other situation most definitely, and we'll do some, but I tend to focus it more on we're in an equilibrium state, our net torque is 0. So we'll do a few problems like this, and we might look at a teeter-totter, classic example, when they're perfectly at rest and you have two different masses on both sides, and you have to figure out where they're placed. Classic example. We have a couple of pulleys, or a couple of wheels that are attached to each other. Let's say this has a radius of 0.1 meter. This has a radius of 0.2 meter. I apply a downward force of 35 newtons on my smaller wheel, and I apply a downward force on my upper wheel, on my larger wheel, and we need to figure out how much force needs to be applied here so that it's in equilibrium. And so if I call this F1, R1, F2, R2, I need to sum up all my torques. Now, so when I sum up all my torques, I'm using the expression torque is RF sine theta. Theta in all cases is 90 degrees. Sine of 90 is 1. R1, F1 is torque 1. Now, this is a positive torque because this is going to cause the wheel to spin counterclockwise. F2 is going to give a negative torque because if this force was all by itself, it's going to cause a clockwise rotation. If this force was all by itself, if F1 is by itself, it's going to cause a counterclockwise rotation. That's how I determine the signs. This is equal to 0. And so we can solve this pretty quick. F1 is R2, F2 over R1. You plug in the numbers, you get 17.5 newtons. If we know, if this was only 10 newtons, then we're going to have an angular acceleration. We need more information to really do anything with that, except to recognize it is accelerating rotationally. But this is how we apply torques, and especially with the signs. If the force, and I look at one force at a time, if that force is going to cause a counterclockwise rotation, that's a positive torque. If this force all by itself is going to cause a counterclockwise rotation, that's a negative torque. So that's how I determine the signs of my torques. In thinking about how I introduced rotational motion, I don't know if I ever really said the difference between linear motion and rotational motion. And so let's talk about that let me just talk about that for a second. A lot of times you're going to see it as linear or translational. A lot of textbooks references use that. So let's compare linear motion with rotational motion, and let's talk about what's going to happen when, because I think this is a reasonable idea to think about. If we have a stick and I'm going to apply a force, and I'm going to apply a force, and I'm going to call it F right in the middle of the stick, center of mass. The stick's going to move up. It has an unbalanced force. It's going to move up. If I apply another force, that's 1/2 that, right in the middle, opposite direction, it's still going to move up. The whole stick is just going to move. And so we have, in both cases, an unbalanced net force, which means we're going to have an acceleration, a linear acceleration. But these forces will not result in a torque because they're right at my center of mass. And so the stick's not going to spin. So in this case, we're going to have only translational motion. Let's say we have the same stick. Force. And then I want to apply a force there. Question is, what's going to happen? When I look at these linear forces, this is in the positive y, this is in the negative y, same magnitude. So from a linear perspective, our net force is 0, which means we have no linear acceleration. But from a rotational perspective, we have an unbalanced torque because of this force. This force is going to result in a torque. This force does not, because it's at the turning point. R is 0. No torque. But I'm going to have a torque based on this force, and it's going to rotate. And so if I apply these two forces to my stick, it's just going to do this. The fact that I think it's tends to be confusing, but when we did force problems, we never looked at where we kind of always lined it up that way, but we never looked at how the vertical and the forces were aligned. If we had a positive and negative, they would balance out. So let's look at this situation. Force right in the middle, small force here, small force here, my vertical forces, my upward force is going to balance my two half downward forces. I have no net force, no acceleration. All my torques are balanced. This does not give me a torque. This gives me a negative torque that results in a positive torque. So my net torque is 0. I'm in equilibrium. It is not going to move. It's just going to stay that way. Now, I got rid of that force. Now what's going to happen? Well, I definitely have a torque because of this. This is not going to produce a torque, but this force will. So I definitely have a torque. So torque is not 0. It's going to rotate. But I also have an unbalance in my vertical forces. I've got more force going up. So my net force is not 0. So this thing is going to go up while spinning like that. I think it's important to be able to look at these types of pictures and describe what's going on from a qualitative standpoint. And you need to be able to look at when we apply linear forces, are we going to have linear motion? We're going to have rotational motion. We're going to have a little bit of both. Okay, the last thing that I talk about in Unit 7A is actually in C mechanics a huge topic area. But we cut it down to a very small amount, and that's dealing with pulleys that have mass. And I keep it, again, like a lot of other stuff with rotational motion, kind of high level, more of a qualitative approach as to what we can expect to happen. We have a pulley with two masses, M1, M2, M1 falls, M2 goes up. And kind of go back and remind them that when the pulley is massless, I'm going to call that T2 and I'm going to call that T1. The tension in rope 2 is equal to the tension in rope 1. And we can figure out the acceleration is just simply the net external force over my system mass, which is M1 plus M2. We had done these problems, we worked it. We had just basically worked them, so hopefully this stuff is still relatively fresh. But this is, the pulley has no mass. Now, need to talk about what if the pulley has mass. And how does this affect things? And what's our end result? If the pulley has mass, and it takes energy to turn the pulley, and we can approach this by looking at an energy aspect, which I haven't talked about rotational energy yet, but let's just think about this. A pulley with no mass, it takes no effort to turn. A pulley with mass takes effort. That effort is force. And so what's happening here is we're not going to have a balance in these tensions like we have with a massless pulley. So let's take a look at what happens when the pulley has mass. When it has mass, and if M1 is falling, M2 is rising, the pulley is turning. It's turning because a force is being applied to it. An unbalanced force. It has an unbalanced torque. Think about this. If this is our pulley, this is tension 1, this is tension 2. If it's turning that way, tension 1 must be greater than tension 2. When the pulley is massless, it takes no effort to turn. T1 is equal to T2. When the pulley has mass, in this case, this tension has to be greater, otherwise it wouldn't turn that way, clockwise. And so we lose a little bit of tension, a little bit of force into the moving the pulley. And so this is going to, that's one thing they need to keep in mind. We have the same external force. Gravity is our external force. That isn't changing, whether the pulley is massless or it has mass. So the same amount of force has to move more mass. Now, this is not as simple as simply saying we're going to add in the mass of the pulley into this equation, but it's similar to that. Because moving mass is increasing with the same amount of external force, we're going to have a smaller acceleration. And that's what they need to be able to look at and describe and communicate, I think, with when we're dealing with pulleys with mass. They should be able to do more calculations when they're massless. These problems, like I said, in C mechanics, I'll spend a couple of weeks doing these problems. They get a little bit more complicated. That's what I have for Unit 7A. I hope that was of some value. Good luck.